So, okay, please go.
Okay.
Sorry,
thank you, Professor Kisby, for introduction.
I'm sorry.
Can you hear me?
I am Professor Quispel, and I will do the introduction. Sorry. Without too much ado, I will introduce Professor Changzheng Chu, who is going to talk about integrable systems and invariant geometric flows in affine-related geometries. Professor Chu, please go ahead.
Okay, thank you for your introduction. So first of all, thanks the organizer, the Nalini and the Georgie for the organization. And,
may I just ask Professor Chu to tilt your camera so I can see your face? At the moment, I only see the bottom half of your face.
Yeah, let me. Oh yeah, can you see my face? No.
No, I can see the bottom of your face. I can see your color.
Yeah, so let me. Okay. No.
Well, you can. If you sit back, I can see your face.
Let me. I don't know how to do that. So.
Okay, no worries. Just keep going.
Okay.
I'm sorry to interrupt.
Okay. Yeah. First of all, thanks Nalini and Georgie for the kind of invitation. So today, I would like to talk about the integrable systems and the invariant geometry flows in the affine-related geometries. So actually, this is a survey talk on the works related to the affine differential geometry. So this is the outline of my talk. So the first I gave the brief introduction and the motivation of the talk. Then we discuss the integrable geometric flows in the Euclidean geometry, central equal affine geometry, central affine geometries, and also the central equal affine symplectic geometry and affine symplectic geometries. If we have time, so we can talk about some results on the heat flows in the affine-related geometries. So the main talk is based on the questions. So the first is geometric realizations of the integrable systems. Second is the geometric formulation of the various properties to integrable, such as the Lax pair, Murat transformation, and the recycle transformation. Also, we would like to know some of the different invariant different equations under the given the Lie groups. We are also interested in the behavior and the singularity and the exact solutions of the geometric flows. So about the integrable curve flows, there have been many results. So sorry, I cannot include all the reference here. So the piano work is due to the Deras and the Hashimoto. So they obtained the nonlinear Schrödinger equation from the space curve flows in the Euclidean geometries. So later, the many the classical integrable system were proved to arise from the invariant geometry flow in other geometries, such as Modi-KdV equation, Ragland equations, KdV equations, Singleton equations, and the Sawat-Koldar equations, KK equations, and many classical integrable systems. So sorry, I cannot include all the reference here. So recently, also the many works to study the integrable curve geometric flows in the such as the Riemann symmetries homogeneous space. So So also there are many works to discuss the discrete integrable curve flows. So in the inverse geometries. So the Japanese group did a lot of work on this topic. So so we are also interested in the invariant different equations in the geometries. So here is we use the when I studied this topic, when first studied the invariant geometric flows in Klein geometries. So here is a definition on Klein geometry. Roughly speaking, if G is a Lie group and H a subgroup, so such as the quotient GH is connected, then pair is called the Klein geometries. So we are interested in the invariant different equations under the Lie group. So here we need the definition of the different invariant. So different invariant of G is nth order the functions, which satisfies the functions is the invariant under the Lie group. Or we can define the invariant forms similar as the different invariant. So in fact, many the integrable equations arise from locally from the evolution equations of this form. So in the Peter Over's book, so there is a result if the G is a transformation group, transforming acting on the space, so product space. If M is a G Lagrange, such as the Lagrange operator is not zero, then every G invariant evolution equations has a form. This here the L is a Lagrange, EL is the Lagrange form. So I is any different invariant of the Lie group. So actually, so such as the KdV equation, KdV and the modified KdV, the local form of this integrable equation can be obtained from this form. If, in particular, if is a projective, if the projective group as F3, so the evolution equations take this form. So if such as the curve shorting equations, of the local curve shorting equations can be obtained if we took the J equals 1. So L is a S square of the E plus is a metric of the curve. So we get the local curve shorting. Also the local KdV equations can be obtained from these equations. So this is so many also the Sawat-Kohdari equation and the KK equation can be obtained from this form. So this is in this talk we are interested in the invariant geometry flows of this form. So gamma is a curve. So Fi depend on the invariant of the curve or the invariant of the submanifold. Alpha I is a frame. So the alpha may be the natural frame or the parallel frame. So in the plane case, so the flow takes this form. So Fg are the velocities, respectively the normal velocities and the tangent velocities. So the first, let us recall the integral curve flows in the Euclidean case. So if we consider the flow, so F tilde, G tilde are the so I say that is arc length So if the flow is governed by this one, so we can find the alkaline element set with this equation. If we assume the S does not depend on time t, so the right hand side is equals 0, so we can determine the tangential velocity by the normal velocities. Also, we can for a closed curve, so we can compute the parameter, get this one. For a closed curve, then we have this one. So in this case, we can do computation for the curvature, so you get these equations. So here the operator omega is nothing but the recursion operator of the mod KdV equations. If f tilde is of the derivative of the chi to the is the derivative of the chi to s alkalines, so we get the modified KdV equations. So also if we set the f is a us is a minus 2 us, k is mu minus uss, so you can get the g given by this one. So here the u satisfies the so-called the modified Kamas-Holm equations. In this series of the conference, the meetings, so there are several talks on the modified the Kamas-Holm type equations. So here we also can get the modified Kamas-Holm equations. So that means the modified Kamas-Holm equation, including the first with the weak for first order term, is equivalent to the curve flows in Euclidean geometries. So also we can get the modified mu Kamas-Holm equations of this form. Here the mu u is the integral of the u over the unit circle. So that means that the non-local modified mu Kamas-Holm equation is the equivalent geometric flow of this flow. So next we turn to the curve, the integrable flows in the Centro-affine geometries. So everything in the Centro-affine geometries is invariant under the Centro-affine transformations. Here A as SL2. Actually, there are two Centro-affine geometries. One is a primitive case, and the second is the imprimitive case. So imprimitive geometries means there is an invariant fluctuations. Otherwise, is the primitive geometries. So here we consider the first consider the flows in the primitive geometries. So here the S tilde is the alkalines, so which is determined by here the S is Euclidean alkalines. So P is a free parameter. So H actually is a support functions of the curve. So we can define the central equal-affine curvature phi given by this one. This is a determined form of the two vectors gamma S tilde and S tilde. So here this is a central equal-affine series-finite formula. So N is a normal vector. So phi is a curvature. So Pinko proved that. So this central equal-affine flow is equivalent to the KdV equations. So this is well-known as the Pinko's flow. So he obtained this result about 20 years ago. Yeah. So also we can obtain the Kamas-Holm equations from the curve flow. Actually, so it's easy to check the Kamas-Holm equation is equivalent to the flow in the central equal-affine geometries. So it's also interesting to study the flows corresponding to some of the particular solutions of the KdV equations. If the Q is a traveling wave solution of the KdV equation, Z is X minus CT. So it is well known that the KdV equations have have the Jacobi elliptic function solutions. This is mean if the right hand of this equation has the 3 different roots, so C1, C2, and C3. So C1 is strictly then C2 and strictly then 3. So we have the corresponding to these solutions. So we can prove that there is it's interesting to ask whether they are periodic solutions corresponding the Jacobi elliptic function solutions. So actually we can prove that for here for m is greater than 3, then infinite many lambda j, so then corresponding curves is closed and has m leaves. So also there are many the other result really corresponding to the solutions of the KdV equations. So yeah, also we have the geometric meaning for the Hamilton structure of the KdV equations. So this is a result is due to the Kalini-Bifa. So they prove that the geometric Poisson structure is reduced to the standard the Hamilton structure of the KdV equations. So it's easy to prove that this Hamilton structure is equivalent to the standard Hamilton structures of the KdV equations. So this provides a geometric formulation for the Hamilton structure of the KdV equations. So to study the relationship between to provide the geometric meaning for mural transformations, here we study the curve flows in the one-dimensional in the real line, also the project space, one-dimensional project space. So as indicated in the Peter Over's book, so there are 3 equivalent geometries in real line, which are described by its Lie group in the following table. So this we call this first is the Euclidean, second is similarity case. So the third one is a project case. So the first one is the Euclidean case is just one dimensional group. So the curvature actually is a k is x prime. So that means n is we can choose the parameter p free parameter. So the k is x is a curve in the one-dimensional project space. So the second similarity case, so the curvature is easy to this is the invariant under the similarity of the 2-dimensional the Lie group. So give is given by this one. So in the third case is the SL2 case. So the invariant is a different invariant is Schwarz derivatives. So this is the third order the differential invariants. So we studied the flows in the last 2 cases, similarity case, and in some books we call the second case also the affine geometry. In practice, there should be the similarity geometries. So the first case is for the similarity case. So we consider the flow is given by this one. This is one dimension. So F is a invariant, any invariant of the chair. Chair is yeah, here chair is this one. So the chair is a curvature. So it's easy to cover if the curve is governed by the flow. So we can obtain the equation for the curvature given by this one. So if F is the first order derivative of the curvature, so you get the box equations. So the operator is the Ricochet of the box equation. So in a similar case. So the box equation is the basic equations in the similarity geometries, that means. So the second case is a KdV flow in the this is SL2 case. Oh yeah, sorry, not similar. Yeah, this is a print error. So this should is a third case is the SL2 also the projective case. So this is the error. This is a projective. This is a should P2 P1. So in this case, the curvature is the Schwarz derivatives. So in this case, so we can obtain the equation for the curvature given by this one. So if F is SP, so we get the KdV equations. So the operator is the KdV equations. So also we can, for the in-parameters, the centro-affine geometries. So so we can project the curve to the one-dimensional case. So in order to establish a relationship between the curve flows in the RP1 and the central equivalent geometries. So we can use the move frame to compute the differential invariance in the central equivalent geometries. So if the gamma is a curve in the plane case, so here pi is a projective from the plane case to the one-dimensional projected space. So here the phi gives it defines the curve from in the one-dimensional project space. So actually, so we can using the Moore framework, so we can prove that this is a Moore-Gardner matrix given by this one. K is actually the Schwarz derivative. So this is so that's mentioned before. So S is the projected curvature of the phi. So if the gamma is a curve on the plane, so we can if the gamma 1 is not there, if gamma, so without a lot of generators, so we can assume gamma 1 is not 0. So we can define the U by gamma 2 to gamma 1. So the general flow in the centro-affine case is given by this one. This is for the plane curve. So R1 and R2 are different dimensions. S is the central equal affine arc length. If the S does not depend on time t, so we get this relationship. So the curve flow is reduced to this one. Actually, this gives the KdV equations. So indeed, we can prove the following result. If gamma is a star-shaped curve by the centro-affine arc length, so U is a projected relation in the affine chart. So the centro-affine curvature set is this one there, I mentioned before. So then U set is this one. So this is the curve flows in the projected. Yeah, so the print error here. So then U, the fulfills the Schwarz KdV equations. My friend, they are this one, given by this one. So they're given by this one. Actually, this really established a relation between the curve flows in the KdV in the one dimensional project space and the curve flows in the two-dimensional centro-affine case. So this also provides a geometric meaning of the Schwarz KdV equations. So this was studied by the Youngman paper and the Kalinin, Abbey, and Belfast paper. So next we study the curve flows in the affine geometry. Some books, the affine geometry is called the special differential affine geometries. So the affine geometry, everything in the affine geometry invariant and unimodular affine transformation by this one in the Planck case. So here is A is SL2, B is R2. So the affine, the series freenet formulas are given by this one. So mu is the affine curvatures, T and N are respectively the tangent and the normal velocity and normal vectors. So if we assume the affine parameter is the invariant under the flow, so here, sorry, the flow is the, which always in the Planck case, we use this flow. So that use this flow. So F is the normal velocity, G is the tangent velocities. So also, yeah, we assume here the rho is the occurrence in the affine geometry, different geometries. So if the rho does not depend on time t, so we can determine the tangent velocity by the normal velocity given by this one. So also we can compute the evolution of the tangent and the normal vectors given by this one. So in this case, so we can determine, we can compute the evolution of the curvature given by this one. So if F is a -3, yeah, so there is a 1/3 here. So we assume the F by the derivative of the curvature to the occurrence. So we get the Savart-Koda equations. So that means the Savart-Koda equations come from naturally from the invariant curve flows in the affine geometries. So here omega is a recursion operator, the Savart-Koda equations. So because there is the operator here, so if we choose F given by this one, so this omega equals the product of this operator and this operators. So this is a recursion operator of the Savart-Koda hierarchies due to the following the operator identity. So it's a direct computation can check the both other equations. So actually this is the original recursion operator of the Savart-Koda equations. So this is the right hand side is a product of this operator and this operator. So this is the curve, integrable curve flows in the affine geometries. So the next, so we study the flows in the centro-affine geometries. So the centro-affine geometries, everything is invariant under the centro-affine transformation. Instead of the central equal affine case by the A in the general linear case. So GL2. So this is called the centro-affine geometries. So here we use the local, using the local form to do the computations. So also we can use the approach similar to the central equal affine case. So this is the local graph case. So here S is the occurrence. So the K is a curvature in the centro-affine geometries. So the Q is given by this one. So if we consider the flow in the centro-affine geometries, T and N is the tangent and the normal vectors. So we find that if for the closed curve, so we need this is 0. Also that equivalent to this one. Also assume the occurrence does not depend on time t. So we find that the G is determined by F by this guy. So then the curvature satisfies these equations. So if F is the director of the K to S, we get the defocus M KdV equations. So this is due to the our work and recently the PAR as Kajiwara cross also the obtained this result. So by the straight the computation, so we sorry, the print errors are here. So the defocusing KdV equations is related to the KdV equation by the Mura transform by this one. So this provide the geometric. So this is the we obtain this is a flow from the in the one-dimensional project space. So this is the curve. This is the flow in the plane case. So this provides a geometric formulation for the Mura transformations in a natural way. So actually here we get the two geometric formulations for the Mura transformations. So one is related different to geometries. Also for one geometries, also for the different curvatures, there is the Mura transformations. I
think there is some. Sorry, can you check your microphone because I don't hear you?
So you can't hear me?
But we can hear you. We can hear
他就
you.
可以是吧？
可以啊，我这儿能听到。
哦，那他可能他的有问题的。
And also here.
Can you hear me?
Yes, I can hear you.
Okay. So there, this is this is a result in the Centro-affine geometries. So to provide the geometric formulations for the metric and all the non-commutative KdV equations. So here we study the curve flows in the central equi-affine symplectic geometries. So what's the central equi-affine symplectic geometries? So so here is the definition for the central equi-affine symplectic geometry for curves. So the symplectic space is a two-dimensional Euclidean two-dimensional space. So it has endowed with a standard symplectic form omega of the symplectic structure. So it's a tangent space is endowed with the symplectic unit product given by so the unit product is defined with the symplectic matrix J. So this is the symplectic the space. So the M is satisfies this relationship. So the J is a symplectic matrix. So we can define the symplectic frame by this one. But this is a two-dimensional vector space. So A1 to AN and B1 to BN. So this satisfies the relationship. So AIJ BIB inner product is 0. This is the same inner product. So AIBJ is 0 when I is not equal to J. So then when AIBI equals 1. So this is the same symplectic frame. This is the same for in the central equi-affine and the affine case. So the rigid motion in the central equi-affine geometry that is invariant everything everything in these transformations. Here the T is a symplectic the group regular motion. So the curve is said to be this is similar to the central equi-affine case. So the curve is said to be the star-shaped central equi-affine symplectic curve if the inner product is not zero. So if the is for any the I equals from I0 to n minus 1, if the inner product is not zero, so we call this is the regular star-shaped curve. So for the star-shaped curve, so we can define the Arclength element by this one. So this is replace the inner product in the. This is the symplectic inner product. So we call this as a central equi-affine symplectic Arclength element. So we can construct the symplectic frame by two. We can construct the symplectic frame by two methods. One is the Grassmmanian, the standard approach. The second is the moving frame method. So this is the moving frame. There are a lot of research on the moving frame. This is due to the Ali Gardin. Later the Griffiths did nice works on the moving frame method. So here we use the notion of the Mark First and Peter Over. So the moving frame is a map from the manifold to the Lie group. So if the action of the G to the manifold, the action is freely and regularly, so there must be a moving frame. So the moving frame can be constructed from the map from the spec specific the space. If one knows the moving frame, so we can obtain all the differential invariants of the groups. So if I is the rho is a moving frame, so the x in the manifold, so we can prove that this action is a different invariant. So also we can use moving frame to construct the symplectic frame in the central equi-affine the symplectic geometries. So here we I don't provide the details of how to construct the moving frame in the central equi-affine the symplectic geometries. So actually we can get the freenet formulas in these geometries. So B is a metric, is a matrix of this form. So to study the invariant curve flows in these geometries, so we need here is a fundamental theory for the central equi-affine the symplectic regular curves. So to study the integrable curve flows in these geometries, we need another frame we call the natural frame or the natural frame. So the natural frame is defined by the A1 tilde to the A2n tilde given. This is related to the freenet frame by this matrix. So this is a matrix. The depend on the sign of the epsilon 2. The sign of the epsilon. So if we using the natural frame, so the freenet formula becomes by this one. So the all the differential invariants in the geometries is are located in the lower triangular matrix. So now we can here the relationship between the this invariant and the orange invariants by this chi1 tilde and p chi tilde and the pi tilde are related to the original invariants by this form. So here we give examples. So we study the 4-dimensional case. So in the 4-dimensional case, so the free-net formula is becomes this one. So depend on the 3 invariants, the p tilde, chi1 tilde, and the chi2 tilde. So this frame is a natural frame. So the flow, the flow is given by this one. So F1, F2, G1, G2 are the velocities related to the different invariants. So using this flow, so we can determine the evolution of the frame, natural frames given by this one. Here A, B, and AB, and satisfy this equation. So the equations for the curvature is this one. More specifically, so we can the equation equivalent to this one. So this is a complete case. Yeah. So here we consider the 2 cases. So one is H2 is a positive. So what's the H2? So this is depend on the so in the 4-dimensional, that means n equals 2. N equals 2. So on the 2, this is in the 2-dimensional case. So this is these are three invariants. So the H2 is this one. So that means if the depend on sum of the epsilon 2 in this case. So if the H2 is a positive, in this case, we get the equations for the matrix given by this one. So using the 2 notations, the gamma AB and the lambda AB. So the matrix KdV equations can be written this one. So actually we can prove that. So this operator, so is nothing but the recursive operator of the matrix KdV equations given by this KdV matrix KdV equations. So this is a result due to the Over and Sokolov in the famous paper. So the flow is this one. So that means this the curve flow is equivalent to the matrix KdV equations. So the hierarchy of the matrix KdV equation can be obtained from the recursive operator, this one. So if the H2 is a negative, so that means the epsilon 2 is a -1. So if we choose B given by this one, so we obtain the Jordan KdV system given this one. So what's the E? E is sorry, I don't have the impression of the form. The E is a constant matrix here. So E is a constant matrix. So doing the geometric flow is good by this one. So if we define the product of A star B given by this one, then we can the system becomes by this one. So this also come from the paper of the Over and Sokolov. So we can provide the geometric formulations for the matrix KdV equations Yeah. Also, yeah, we can get the recursive operator in this case given by this one. Yeah, this is the recursive operator of the matrix KDV system. So this is also so we can study the invariant integrable curve flows in the affine symplectic curve flows. So in the affine symplectic curve case, so the frame is the same in the central equal affine case. So this is constructed. Was constructed in the paper due to the Cameron over and the Tannerblatt. So they also defined the star-shaped the central equal affine symplectic curve. If they satisfy this, here X is the free parameters. So also can define the central the affine. Oh, this is arrow, yeah, print arrow. This should be the affine symplectic curve. The arc length satisfies this one. So this is the affine symplectic arc length parameter defined by this one. So the Freenet formula is about the same as the central equal affine case. Central equal affine case. So what the questions? What's the corresponding the integral geometric flows in the affine symplectic case? So the evaluate study the geometric flows in the affine symplectic case given this one. So AI is the affine symplectic frame. So actually, the evaluate proved evaluate is a student of the Peter Over. So they proved that the invariant geometric flow in the affine symplectic geometries, if they preserve the symplectic arc length, prove that it is a form given by this one. So also the corresponding to this flow. So the different invariants in the affine symplectic case are the H, I, and J. There are three different invariants. So the different invariants send with very complicated systems given by this one. So here V1, V2, V1, V2, and V3. Yeah, sorry, is arbitrary. So yeah, should be yeah. Also there should be V1, V2, V3 given by this one. So this is a very complex case. So depend on this guy's C42, C72, yeah, given by this one, given by this. So the questions: what's the integral system from this complex systems? In the very simplest case, so is given by this one. If the gamma t is A1, so this flow is equivalent to it gives the bihamiltonian systems. Here the H1, H2 given by this one. So P1, P2, yeah, here I didn't print that. Also is a bihamiltonian operators. So this is the integral systems. So which is equivalent to the given by this one. This is a rational integral system. So this system has a bihamiltonian structures. So the question here is how to classify the integral systems of the 24 for these complex systems. So this is the integrable curve flows in the affine-related geometries. So Excuse me, how much time I have? Maybe 5 minutes.
At the most, I would say.
Okay. So also, another we can start another geometries. We would like to provide the geometric formulations for the matrix modified KdV equations. So we can study the curve flows in the Symplectic grammar space. So in this space, we can provide here, we don't have time to give the details. So we can provide the geometric formulations for the matrix modified KdV equations. So this is so we in this geometries. So how to construct the frame? So this is complicated. So we can adapt the moving frame method. We can construct the frame in this geometries. So because of time, so I don't have time to give the details. So finally, so I just to mention the two heat flows in the centro-affine geometries. In affine geometries, so the heat flow, gamma t equals gamma ss. So the curvature satisfies these equations. So if we use a local graph, so we get these equations. So, but in the central equal affine case, so we get the heat flows equivalent to the we would like to study the curve, the heat flows. We want to know using study the invariant equations and the centro-affine transformations and the centro-affine transformation. So we get the same equation for the curvature, but the support function actually satisfies different equations. So that's is different from the affine case. So also for interestingly for the heat flow in the central affine geometries. So the heat flow is equivalent to the box equations. So that is completely different from the affine case. This is the affine case. This is the affine case. So, but for the central equal affine geometries, so the equation for the curvature is the same, but for the support function is different. But for the heat flow in the central affine geometries, so we get the equations of the visit the box equations. But these box equations, so we can solve with the characteristic method. Depending on the equation for the metric, so that means the central affine metric, we can solve these equations. We can also get a similar result in the central equal affine case. So this is the result for the heat flow in the central affine curve flows. So this is so we can also prove that if the curve converges most to a point when the t goes to infinite. So this is something like for the central affine case and the affine case. So I think I should, because of the time, I stop here. Thank you for your listening.
Okay, thank you very much, Professor.
Too many things.
Thank you very much for a very interesting survey of invariant geometric flows in affine-related geometries. So are there any questions at this point? Maybe I will start with a question myself. You have talked about a lot of equations that are related to, or structures that are related to KdV and MKdV and Sawada-Kotera and equations like that. But as I understand it, there are also other integrable partial differential equations, such as the nonlinear Schrödinger equation and the Heisenberg spin chain that can be looked at in a similar approach. So can you say anything about that, how that fits into this kind of analysis? Do they correspond to different geometries, or how should I think of that?
So the Heisenberg spin model and the Schrödinger equation come from the space curves in the three-dimensional Euclidean geometries. So actually, there are many methods can be used to study recently the many works to study the geometric flows in the for the nonlinear corresponding nonlinear Schrödinger equations, also the Heisenberg spin model. So what do you mean? So that you mean the?
Well, I was wondering if there's some sort of similarity between the work that you have been doing and the work that people have been doing on the nonlinear Schrödinger equation and the Heisenberg spin chain.
Yeah.
Oh, well, Wolfgang Schiff says.
Yeah, this is today. So I will discuss mainly on the planar curve flows. Yeah, using geometry. Also, we can study the space curve flows.
Mm.
Also, even the hypersurface flows in this geometry.
Right.
So for the space curve flows, so we can get such as the Bosniansky equation, Tezaki equations, and so they are for the plane curves, they are in the affine geometry, they are the many works on the analysis. So, but I don't know for the space curve case. Are they similar?
Okay.
I have a question, Reinhard.
Yes, Peter.
So I was wondering where the integrability comes in. So you start with a Lie group action. You have an evolution of a curve flow, and there is always a corresponding evolution of a curve of the curvatures of that curve. And you can obtain that relation through the moving frame indeed. But this is quite a general thing. It does have nothing to do with integrability. You can show that the two equations, the evolution of the curves and the evolution of the curvatures are related. And also that symmetries of those equations are related as well, but that is irrespective of the integrability. So I'm wondering how you would obtain the integrable cases and whether you claim any completeness in that sense that you have all the integrable cases. We saw many examples, but yeah, so can you comment on that?
Oh yeah, many people ask similar questions. Yeah, so I don't know what conditions can guarantee the integrability of the curve flows. So I don't know. Yeah, even yes, many people. Yeah, even the Peter also always ask me the similar questions. and how to guarantee the integrability. For generate, you mean that generate the integrability of the curve, general curve flows?
Well, there's a general relation between curve flows and curvature flows. That also for non-integrable curve flows, there are non-integrable curvature flows. But the thing is how to get to the integrable cases.
You mean that what conditions? You mean under what conditions?
Well, for example, in your equation for where you obtain KdV, you take an arbitrary function, which is, you denoted that by f, and that can be an arbitrary function of all the curvatures, of all the Schwarzian derivatives and their derivatives. You take a very specific relation. You say that f is equal to, you know, the first derivative of the partial derivative, and that will give you your integrable case. But that's a very specific relation you take. And you know, where does it come from?
Maybe so we need to add some you mean maybe if for the physical case, maybe so we can add the conditions for the, but I don't know for the geometry.
May I interrupt for a moment?
Yes, Nalini, please do.
It's just that it's 6 minutes past the hour for us, and so I think probably Peter's question could be explored at length, perhaps by direct communication, if you don't mind me suggesting that. And I just wanted to make a few words, say a few words, because this is the last APIOS seminar for the year. And I wanted to thank everybody for coming to the seminars, but I wanted to in particular thank Giorgio Gubbiotti, because he's the person who came up with the idea and has been the engine behind the scenes, making sure that everything is well organized to make it happen. So we started this series, the Asia Pacific Integrable Online Seminars, in June this year. We've had 11 seminars so far with speakers from Japan, China, Australia, and even Czechoslovakia. And I hope you agree with me that it's been a very interesting series of seminars. I think everybody in the Asia Pacific area has been, I think, enjoying participating. So it certainly met a need. So I want to thank everybody, and in particular Giorgio, and hope to see you again next year. Please take a look at the APIOS webpage and check the details of the next one. I want to also thank the organizers, Murray Batchelor, Ray Inui, Kenji Kajiwara, Kenichi Maruno, Sarah Post, and Dajun Jung for being involved in the setting up of this, this series. One last thing is that we are also having a workshop next week, an online workshop on integrable systems through the Sydney University group. And I sent you a chat about it a little earlier. Please take a look. And if you'd like to have more details, please feel free to contact me and Giorgio. So thank you.
Thank you, Nalini.
So thank you, Nalini, for the organization.
You're very welcome.
Thank you very much.
Okay, then I think I will thank the speaker again, and I look forward to seeing you all next year again. Thank you, and have a good Christmas and New Year, and see you in the new year.
Good. Thank you. Bye-bye.
Bye.
Oh, thank you. Thank you very much.
Thank you everybody for coming.
Bye.
Bye.